Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is section 4.1 on multiplicative inverses. Specifically, we'll be looking a lot at multiplicative inverses in modular arithmetic, like z mod 5z or mod 5. So let these bars represent, for now, arithmetic mod 5. So a chunk of a merge where we're merging multiples of 5 with 0, and it preserves addition. So hence what we're going to have is like 2 bar. That's all the numbers that are 2 more than a multiple of 5. They're all merged together and so forth. Now we have this nice arithmetic because on the fibers or the fiber chunks, there's only 5 chunks in here: 0 bar, 1 bar, 2 bar, 3 bar, and 4 bar. And we have a nice arithmetic between them because multiplication after we merge is defined on how it happens before the merge in such a way so the multiplication is preserved. So doing it after or before, under the bar or separate the bars, it'll be the same. So 2 bar times 3 bar we can define to be 2 times 3 underneath the bar, which is 6, which is 1 more than a multiple of 5. So it's just 1 bar. Okay, so here's a question. Can we find something like 2 bar that we can multiply to 3 bar so that we get 1 bar? 1 bar is kind of, when we multiply by 1 bar, that's the identity. It doesn't do anything to anything else. It 1 bar times 2 bar is just, for instance, going to be 1 times 2, so 2 bar. It's just preserved. It's like multiplication by 1. So it's like 2 is kind of like the number that we can multiply but to 3 to get back to 1, kind of like it's reciprocal. Like imagine 3 times a third is 1, right? So 2 bar is like a multiplication inverse for 3 bar. And in general, we have a we want to be able to do this just completely and totally. In general, can we find inverses of things? And that's what this section is going to be discussing. Here's an example. What if we have an equation? We want to solve this equation. Well, you see this 3? We can imagine like multiplying by a third on both sides or dividing by 3. That's like multiplying by the inverse of 3. So which is 2 bar in this case. So multiply both sides by 2 bar, and then that guy goes away. So we just have x bar, and then we just get negative 2 bar. So we were able to compute what x is in this equation using the idea that we have inverses. That's one use of inverses, and there's other ones too. Okay, so we can't really divide by 3 in z, right? But it's funny because when we do this merge on z, we all of a sudden can divide by 3. Dividing by 3 now is the same thing as multiplying by 2. So kind of interesting that all of a sudden by merging, we've actually added structure in, so we can like have multiplicative inverses all of a sudden. And that's kind of a neat idea. We use that idea a lot with cryptography and other things when we're encoding. All of a sudden we've taken the integers and we've produced the structure on them so that we can like invert what we're doing a little bit. So okay, so let's take a look at this right here. Let's suppose we want to find the multiplication inverse of 5 bar in z mod 43z. Okay, so let's see how that would work. Okay, well, here we're trying a process. Let's try to multiply 5 by something that takes us as close as possible to 1 bar. All right, so I know 5 times 9 is like 45, which is 2 more than 43. So well, that's a start. It doesn't quite get me to 1, but that's okay. because think about it, 5 times 9 is 2 bar. Then we've actually reduced our problem to finding the inverse for just 2 bar. And let's think, 2 times what gets us close to 43? Well, notice that, when you get to 42 would be nice. So 2 times 22. In fact, we can see that. So 2 times 22, that would be 1 bar. Hey, so 5 times 9. Okay, well, look, we just found the inverse of 5 bar. Not too bad. Kind of the idea was we just intuitively were thinking, all right, what takes us close to 1? And then once we get there, we get that thing, and then just start from there to get, and it works nicely to just kind of go through that particular process. And then here, this is just a computation to discover that 26 bar is the result of that multiplication. All right. So let's kind of detail what we were doing with the diagram. So say 5 times 9 to get something smaller. So here you see this 5, 2, 1. We're getting things closer, representatives that are closer to 1 by multiplying. So we find something that is closer and multiply by something else to get us even closer, even to get us spot on. So then the inverse would just simply be 9 times 22, as we calculated right here. 9 times 22 right here, and we get 26 bar. Okay, so 26 bar times 5 bar would be 1. Okay. So, and we can use this notation for multiplication inverse. So it's kind of like reciprocal notation here. And essentially that's kind of the idea. Okay, so let's look at this example right here. Let's try to find the inverse of 7 bar. So we try the 7 times what? So 7 times, we want to get close to 1, so close to 1 more than 32, which is 33. So basically close to 32. So we think multiples of 7. What multiple of 7 gets us me close to 32? Because 32 is close to 33, right? Which is 1 more. So is there something that gets me close to 32? So I think 7 times 5 gets me close. In fact, it gets me 3 more. 3 more than 32. That's good. Then we look at 3. 3 times what gets me close to 33? And notice that times 11. Hey, that's 1 more. Hey, we did it. So that means that if we say 7 times 5 times 11, that would get us to a representative that is in 1 bar here, 1 more than a multiple of 32. So if we just multiply 5 and 11 together, we get 55. 55 bar will be the ticket that we can reduce that. This is just a little, we can even subtract by 32 and it be in the same bar, because 32 is a multiple of 32 itself, and we get that. Okay, so we have an inverse. Now, let's do something else. Let's try to find the inverse of 11 bar in Z mod 24Z. And so we proceed. 11 times what gets me close to 24? Well, 11 times 2 gets me to 22. Aha, so that's like 2 less. And then 2 less, so 2 times what gets me close to 24, and I try like 12. In fact, maybe I should try like negative 12, because that give me spot on 24. What's that? 0, I don't want that. I actually wanted it to end up at 1. This is a problem. Notice how we're getting to 0 here. It doesn't quite work. I guess we could have even, yeah. Even multiplying by 12 takes us to 0, because negative 24 is 0. So yeah, that would work, but I guess it's to 0, but that doesn't really work, does it? Because we wanted 1 in the end. Once we're at 0, we can't really do anything, because we're just going to stay at 0 there. So this process isn't foolproof, is what we've seen. We have to be slightly careful. Notice that right here, we've made a mistake even, because see this multiplication by 2. 2 is actually a factor of 24, which 12 shares a factor with 24 as well, or it is a factor. Notice then when we keep going, we'll be able to we're going to be getting to 0. So kind of the idea is we stay we stay away from when we do this process, we stay away from factors of 24. We don't want anything to share a factor with 24 that we choose. So if we can try this again, instead of using -2 like we did up there, or just +2, instead of using 2, why don't we use 5? 55, so kind of look at another multiple of 24, like 48. 55 is 7 more than 48. And at least we've reduced. Notice 7 is less than 11. That's closer to 1. So it's a little better. Okay, so 11 times 5 takes us to 7. 7 more than a multiple of 24. And then we think 7 to 24, we can go, okay, so if we multiply by 7, we get 49. Hey, 49 is one more. We've done it. Okay. So that works. I mean, there's various other options we could have done. We could have done, let's see, if we did, let's try to think about this. If we did 7 times 3, but wait a minute, is 3 a multiple of, oh, but 3 is a factor of 24, so we can't do that. Notice strategically, we have to stay clear from that. We don't want to choose 2, we don't want to choose 3. So we have to kind of, if we need to look at other placements around other multiples of 24, that's fine, like 7 times 7. And then we'll end up getting there. As long as these numbers are going down here, we're good. So then we can compute this. So we got to stay away. Now, that being said, what if the number here actually shares a factor with what, like with 24? We are already in a problem that we can't get out of, and we'll never be able to get an inverse. So this number that we start with already has to not share any factors with the beginning guy. So like this 24 thing that what we're modding out by, the mod guy. It can't share any factors with that. And then as we go along, the numbers we choose right here, they can't share any factors either. And then we will get down eventually in this process. These go down and we will eventually get down to 1. Okay, here's another example. So let's find the inverse of 7 in mod 16 arithmetic. And notice that, so how do we get close to 16? Well, if we multiply by 2, but hey, that's not nice. Yeah, 2 is a factor of 16. So maybe we look at thinking of this again. Why don't we do something else? If we go 7 times 3, that's 21. And hey, 21 is 5 more than 16, and still, at least this number's gone down. That's okay. Then we say 5. Hey, 5 times 3 is 1 less than 16. So we put a -1 and then multiply by -1, we get 1. That works great. So we can see the inverse right here. And actually, it's its own inverse. 7 bar is its own inverse in this case. So that's something that doesn't happen in the real numbers unless you're at, let's see, 1 or -1. -1 times -1 is 1, and 1 times 1 is 1. Those are the only numbers that can happen with if you're just looking at the real numbers. But here, when you merge on Z, you get fun things sometimes. You get other guys that are their own inverses. Multiply them to themselves, they're 1. Okay, so that concludes our little read along on subsection 4.1.1. Thanks for watching.